Hello everyone, welcome back to the Python full course. I hope all of you are doing great. So before we begin today's lecture, let's quickly revise the important concepts that we covered in our previous classes. So far we have learned about Python tokens, keywords, identifiers, literals, and variables. So these topics form the foundation of the programming language. Out of these, I want to point out something very important, that topic like Python history, features, applications, then the version character sets and all. These are some theoretical concepts which are extremely useful from the perspective of your academics and Viva. But during your practical exams or interviews, these concepts are like often asked. So they are definitely worth learning, but when it comes to the actual programming part, the concepts that you will use every single day are keywords, identifiers, then literals, variables, expressions, and operators. So every Python program you write will depend on these building blocks only. So that's why from today's lecture onward, we will start shifting our focus more toward writing the code rather than just memorizing things or understanding the theory portion. So today's topic is operators in Python. So operator allow us what? By the name itself, it allows us that it perform different kind of operation on data. Whether you are adding numbers, comparing values, checking condition, assigning values, or working with even bits. Operators are involved, in fact, almost in every Python program. And almost every single Python program uses these operators in one way or another. As we move forward in this course, you will also notice few another changes that until now we have been using PPT presentations quite extensively because we were covering many theoretical concepts that required explanation. So, but from the upcoming lectures, the use of these PowerPoint slides, I'll reduce them gradually because the reason is simple. We are learning programming. So, programming is not something you master by listening to the theory. It is something you master by writing the program or writing the code. So, you can watch someone explain Python for hours, but until you write the programs yourself, you will still make mistakes. You won't be able to debug things on your own. You should experiment, you should debug them on your own, you should make mistake and come up with different ideas. Real learning doesn't happen just by watching lecture. So from now on, our lectures will become much more practical, I'll say, and we will spend more and more time to dive deep into the Python. So we will learn how a few shortcuts. We will also learn other functions, methods, and everything by writing the programs. And we will also observe the outputs and understand how Python behaves in different situations. So I encourage all of you to keep your Python editor open while watching these lectures from today. It's mandatory. You should do it because it will enhance your learning. Don't just watch me while I'm writing the code. You should pause the video, see the question what I'm trying to do, and then try to implement on your own. If you fail, that's okay. That's completely fine. Unpause the video, play the video, and see what I did. And understand what happened, and then read and try to re-implement it. We can have different approaches for same problem because that's how we world works. There can be multiple solutions for a single problem. So without wasting any more time, let's begin today's lecture and understand one of the most fundamental concepts in programming, that is operators in Python. So here you can see that something special in Python programming. So what is so special about it? Let's find out all together. Here you can see that operators are the tokens that trigger some computation or action when applied to some variables and other objects in an expression. So now here you can see there are 8 types of operator. I have categorized them, where you can have read the name. This is unary operator, this is a binary operator, then bitwise identity, relational assignment, logical, and membership operators. We will learn every type of operator, and you will also get to know that some of the operators are repetitive in nature. That there might be an operator which is in unary operator and also in our this bitwise operator. Then you will see, oh, it can also be in a can be a binary operator. Then it can also be an assignment operator. So these are a few things you will get to know. Now, these these symbols, these contains all the operators that we will be learning in the today's lecture. So starting with the very first, which is unary operator. What does unary suggest? Unary, by default, the word suggests that something which is one unit itself, that's it. So the definition says operators which require one operand to operate upon. So we came across two terms. One is operand and another is operator. The operator needs an operand to do the operation. So let's say, for example, if you are in a hospital, there will be a doctor, there will be a patient. So the doctor is an operator and the patient is an operand. After performing the operation or the medical actions, whatever output will be achieved will be the result. So likely here the things or the literals over which the operation is done over is an operand. Now we have four types of unary operator. One is plus, one is minus, another is bitwise, and the fourth is not. Now, what does these do? Let's have a look over there. So I have opened my code editor. You can see, and by the end of this lecture, we will also solve these questions. These are something 100 questions. We will go through all of them and we will try to solve them as soon as possible. And these the 10th section G, which is I'll keep it for you. You guys will try to solve it. If you are able to solve it, well and good. Otherwise, I'll post the comment with the solution for these. And this is the challenge questions which you need to predict the output. I'll display them. Don't worry about it. So let's get back to the topic we were discussing, unary operators. So we got four unary operators, either plus, minus, bitwise complement, or the negation, which is our not operator. So it means that I'll open the direction. Now you will be able to visualize it much more better. So let's create a variable a is equals to 10. Now what has happened here? We have created a variable or an identifier with a variable with a character small a, which ASCII equivalent is 97, and I have assigned a value 10 to it. If I do print plus is equals to a, sorry, so what will happen? This is nothing but this is the unary operate the plus unit. This is the unary plus. So unary plus does nothing but it will give you the result as it is. It won't do any change. If I try to do it, here you see plus 10k. Now I will create another variable b and I'll assign minus 10 to it. and now I do print plus b, some of you might think that it will give you plus 10, but no, nothing like this will happen. It will give us minus 10 only. So now we have variable a is equal to 10 and variable b is equal to minus 10. So now we understand that how the unary plus behave. Now it's time for the unary minus. Unary minus do uh, act exactly opposite of what unary plus do. Unary plus don't do anything, but unary minus, it just changes the value of the value passed. It changes the sign. So if I do print minus a, the output will be value stored here is 10. So after changing the sign of the value, it should become minus 10. So the expected output is minus 10 and we will get minus 10 only. If I run this, here you can see print minus 10. Similarly, if I do b is equal print minus of b, then also we will receive a plus 10. Why we will receive a plus 10? Let's understand. Here you can see minus 10 and the expected output is plus 10. If I run this, here you can see plus 10 came as output. Now let me close the terminal and so that you can have a better look. So we got this. So why we call them unary operator? Because to operate over something, it only needs one operand. So I can do plus 5, I can do minus 5. It won't throw an error. But can I do and 5? If I do and 5, see the cursor by default came to the new line and it is showing something and unexpected. It expects an expression before the and. And if I try to enter forcefully, here you will see a syntax error came because and is also an operator, but it's not a unary operator. So, but we know that not is a unary operator. So if I do not true and I run this, I'll get false because it's a valid syntax. And not here is acting as a unary operator, which is logical negation. Logical negation, the word itself defines its meaning that it logically negates whatever is told to it. If you say true, it will say false. If you say false, it will say true. So that's how our not operator works, which is a logical negation, which does logical negation. Now we have bitwise complement, which is referred with the help of this symbol. Now, if I do bitwise complement of this number, mathematically or algebraically, I'll receive minus 10. Not minus 10, but minus 11. And why I received minus 11? Because it is the complement of, it's one's complement of the value. So we will understand what happens when we will learn how we operate it over binary. So keep this in mind. And if I do this, you will receive 9, which is a value less than it. When we will learn how binary works, we would be easily able to answer why this behavior was there. So let's move forward to the next operator, which is the binary operator itself. But before that, I need to make you understand that how we convert a integer to a binary. So the math is very simple. Let's say I have 21. So I need to divide 21. So if I need to divide 21, how I'll do? 2 ones are 2 and then 2 zeros are 0, 20 will come here and the remainder will be simple. Remainder will be 1. So instead of doing it like this, uh, give me a second. Instead of doing this like this, what we can do is we will keep dividing the number now, and we will write the remainder on the right side. Now 21, 2 divided by 2, we got 0, nothing in remainder. Then output will be 10, and remainder I got is 1. If I again divide it by 2, the remainder will be 0, and the quotient will be 5. Now again quotient is 5. If I again divide it with 2, I'll get 2 and the remainder as 1. And if I, sorry, here it will come 2 because 2 to the 4, 4 plus 1, 5. Now if I divide it again, remainder is 0 and the quotient is 1. Now as we get to this 1, we stop dividing because dividing it further doesn't make any sense. Now we will write the value in this order, just from bottom, from here to the top. If I zoom in, so we will write values from here, then from here, then from here, like this. So the first value is 1, then the 0, then 1, then 0, then 1. So this is the binary equivalent of 21. In the previous lecture, I also told you that we can get the binary value by using this. The binary equivalent of 21. If I try to get the value, you can see 10101. So that's how you can do it. If you try to, can we do this 0b, then 10101? If I try to do this, you can see a traceback error because an invalid literal for int was passed because int can't do typecasted. But what if I pass 67? Not 67, but I pass 10245. It will typecast it because it's a number for it. It will do the thing. Won't behave weirdly. Now we are done with this. Here you can see that from the left there are total 1, 2, 3, 4, 5. Total 5 values we have. Total 5 different indexes. So the rightmost index, we will say it is 0th index. Okay. So for binary, for learning binary, we will consider it. This will be 1. This will be, we were having 0, 1, 2, 3, 4. So 4, 3, 2, 1, 0. These are the values. Now, as we are converting it to the binary, so the base number will be 2. So base is here 2. So to again convert the binary value to an integer, what you will do, you will take the binary equivalent digit of that place. So, and you will just keep multiplying it with 2 to the power 4. Like, see, now here we have 1. So we will do 1 into, now the base is 2. So we will multiply it with 2. And the power is here, the power here is 4. So I'll just raise the, so I'll multiply it with base of 4. Then I'll add it. Then what I'll do, here you'll see it's 0. So 0 multiplied whatever. So, but for better understanding, we will do 0 multiplied by 2 to the base 3. Not to the base, but to the power 3. Later on, we will add. Here you can see again 1. So 1 into 2 to the power 2 plus 0 into 2 to the power of 1 plus 1, not, yeah, yes, it's 1 into 2 to the power 0. So this will be the expression. If I try to uh, evaluate it, what will come? Any guesses? Here you can see 21 came. So this is the method you can convert any binary back to its integer form. So for example, I have 1001. So how you will convert it back to integer? What will be its binary equivalent? Not binary equivalent, but integer equivalent. So how we will do? Here you can see it is 0, 1, 2, 3. So now 1 into 2 to the power 3 plus 0 into 2 to the power 2 plus then again 0 into 2 to the power 1 plus 1 into 2 to the power 0. Here you can see if you will try to evaluate it, this will be 1 itself, these values are 0, and this value will be 8. So 8 plus 1, we will get 9. If I try to find the value by binary equivalent of 9, you will see I'll get 1001, which I guessed. So that's how you can type convert the value. Now, when we use this function, this operator, which is bitwise, bit, bitwise not when we do. So what it does, it just swaps the value. So wherever it's 1, it will make it 0. Wherever it's 0, it will make it 1. Wherever it's 1, it will again 0. So 0, 1, 1, 0. Now, this is equal to 9. If I try to solve this value, so this is 0, 0 plus 2 plus 4, which is equal to 6. Now, here you can see it is 6. But if I try to run it on here, will I get 6? No, I didn't get 6. Now I'll explain why this happened. Because binary is not just this much. Binary will still have 0, 0, 0, these characters in front of it. So there is a concept of having highest significant bit. So there is a thing called highest significant bit. So this is 0, 1, 0, 0, 1. This is this is not the complement of it. So now how this thing works, here the last bit gives the sign of the integer. So this will be -2 when we will be evaluating the value after us whenever the non-truncating zero start, the very first non-truncating zero will be the most significant bit if it's a positive value. Okay, so now here this is 0. So how we will calculate it? We will calculate it as -2 into 0, 1, 2, 3, 4, 2 to the power 4 plus 2 into, sorry, my bad, -2 into 2 to the power 4, then plus 2 into 2 to the power, not this, sorry, my bad. So this is 0. So this is -0 into 2 to the power 4. Oh, that was, I was confused that why it is happening like this. This is not something which should be there. So here it is 1. So 1 will come. 1 into 2 to the power 3 plus 0, 0. We got 2 zeros. So I'll just negate them. I'll not consider them for now. Then 1 into 2 to the power 0. So this is 0 itself. This is again 2 to the power 3, it's 8 plus 2 to the power 0, it's 1. 8 plus 1, it's 0. But now, if you solve this thing at the most significant bit, it's 1. So, what will happen here? We will take minus 1 into 2 to the power 4 plus, again we have 0, so we won't consider it. 0, 1, 2. So we have 2, 3, 4. So 0 we won't consider, we will consider only power 1, power 2, and power 4. So for power 2 to the power 4 plus 2 to the power 2. To the, sorry, my bad, 0 2 to the power 1 and 2 to the power 2. Is there, and for 2 to the power 4, the most significant bit is 1, that means it's negative 1. So what will happen here? This will give us 2 to the power 4 is nothing but 4 into 4, which is 16. So we will get minus 16 here. Plus 2 to the power 2 is 4. Plus 2 to the power 1 is 2. So 4 plus 2 is what? 6. Minus 16 plus 6, minus 10. Now if I do this again, which is complement of minus 10, you will get 9. Why you got 9? Let's find out. Here, to make binary equivalent minus 10, let's try to write binary equivalent minus 10. Here we'll see 1 0 1 0. So this is what? Minus 0 1 2 3. This is 8. This is 2. 8 plus 2 it is showing with, okay, so it is basically showing us binary equivalent with a minus in front of it. So we know 1010 is binary equivalent of 10. So, but to get binary equivalent of minus 10, let's find out. So how we will make it? We can't do it with minus 8. We can make it with minus 16 plus 6 we need to make. So binary equivalent of 6 is what? Let's find out. Binary equivalent of 6. If I do it, it's 110. So it's 110. Now 0, 2, 4, 0, 1, 2, 3. It will be like this: 1, 0, 1, 1, 0, 0, 1, 2, 3, 4. Beautiful. So the binary equivalent of minus 10 will be like this. If I convert the values, so it will be 0, 1, 0, 0, 1. If I try to convert it back into the integer, I take the ones complement. Ones complement we did. This thing we operated over this value. So we got this. This is what we got: 2 to the power 0 plus 0, 1, then 2, then 3 plus 2 to the power 3. So these are the values which are of some use for us. So this is 1 plus 8. We got 9. If I switch to this, you can see negation, after operating the bitwise not over minus 10, we get 9. So that's how we work with binary. Keep this in mind. You need to practice it a lot so that you become very fluent with it. You need to know how to convert integer to binary and binary to integer, how to use bin oct, and how to play in between these. Then with this, you can convert it into hexadecimal, octal, and many more. So you should know about it. getting back to the actual topic again, which is our operators. So we were doing bitwise operators. Very first was binary, but we will do bitwise so that binary will be not that tough for us. So in bitwise operators, we have, by definition, it says operator that perform operations on the binary representation, also known as bits of integer. So these are the all the operators which you can use. As in the previous lecture, I told you about two operators, two keywords, which were and or, and I showed you a truth table. So it is this and this or is equivalent of those only. So if I try to do it, let's say we want to do 5 and 7. Now the binary equivalent of 5 is what? Let's try to understand. Binary equivalent of 5 will be 101. So we will write 0101, and binary equivalent of 7 will be it will be 110, but I'll still, oh no, it's 111. Ah, yes. 6 will be 110. So if I, sorry, my bad. If I operate and over this, so what does and do? It gives us only, uh, I'll make truth table of and. The truth table of and is this. So if both the values are 0, x and y, let's take, and the result. So if both the values are 0, it will be 0. Either is 0, it's 0. So it gives only a true value of 1 whenever both the values are 1. So by this table, if you see here 0, 0, it will give 0, 1, 1, it will give 1, 0, and 1 again. Now, do, if I try to resolve this back to the integer, what I'll get 2 to the power of 2 plus 2 to the power 0, which is 4 plus 1. What will I get? I'll get 5. Okay. Now, if I try to run this, I do 5 and 7 I did. So here you see 5. So that's how you know that how bitwise operator and works over the integers. Likewise, we have the OR operator, and we use OR in binary with the help of this pipe symbol. So which is just above your enter on the right side. So if I do 5 or 7, let's try to predict the result. Now we know 0101 and 0111. The truth table of and we know, or we will learn the truth table of or. I'll paste it here. Only difference is that here this will be also 1 1. Remove these. With the help of this table, we will do now. If I do this operation over this is OR operator basically. The output we are expecting is 0, 1, then again 1, then again 1. What is happening? This is 1, 1. So, so these are 1. So we got 1 as output. These are 0, 1. Then also we got 1 as output because it's an OR operator. but these two were 0, so that's why we got 0 as output. Now if I convert it back into an integer, what will I get? So this is what? 2 to the power 3 plus 2 to the power 2 plus 2 to the power 1 plus 2 to the power 0, which is 1 plus 2 plus 4, which is 4, 5, 6 plus 1, 7. So we should expect a 7 here. If I try to run this, see 7 we got as an output. So that's how it works. You can try to experiment it out with more. If you are unable to understand any certain example, do let me know. I'll make a short video. I'll upload it with a clear understanding so that all of you get whatever is happening. So this is how the bitwise and an or operates over a certain integer. Now we have XOR also. So how do we use XOR? We use this special symbol to operate over numbers. So if I do 5 XOR 7, if any one of you have completed your 12th from CBSE or ICSE, in physics you must have learned about logical outputs, logic gates. So you must have an idea what XOR are, but don't worry if any one of you haven't studied it, I'll still teach you. So this is 5. So now we'll learn the truth table of XOR first. Table of XOR is both the values should not be same. Either of the inputs should be different. So this is XOR, and there is another operator which is XOR, but it's in ECE. It's not for us. To make a XOR operator, you can just use the bitwise NOT and XOR all together. So let's do it. We know the not the let me copy paste. Bind equivalent of 5 and 7 is here. Now we will use a different operator, which is XOR right now. I clear this. Now 0 and 0, here you can see it will result in 0. 1 and 1, it also will result in 0. 0 and 1, it will result in 1. And 1 and 1 again 0. So the output we are seeing is a 2. So if I try to run this, see 2, it's as simple as that. We should know how to convert an integer to its binary form. Then you will be able to easily verify or understand that, okay, that's how it's happening, nothing special, no rocket science. So we covered these topics, which is we covered our unary operators. Now we are on bitwise operators. We will go through binary operators, but we have already used many binary operators. The things which are new to you is modulus. So I'll tell you what is modulus and the exponent also. Don't worry about it. And here one thing I want to fix. Just give me a second. That the symbols are quite misaligned. So don't get confused with it. Bitwise operator. So now it's fixed. So this is the uh, correct binary operators with their respective name. The modulo, flow division, and rest I think we have already used once, so it won't take much time. We should focus on bitwise operator because it's very important. It might come in MCQs. You should know how it works. So we covered AND or XOR, and bitwise not. You already know that it just negates, just converts the value. If it's 0, it will make it 1. If it's 1, it will make it 0. So if I do I'll get a -1. Why I got a -1? Because logically, what is happening here? The binary equivalent is like this something. So what will happen? It will make it something like this. Now the shortest form I can use is just the singular values. Now this is the most significant bit, and the most significant bit carries the sign. So this is what? This is -2 to the power 0 into 1. This is what? -2 to the power 0 is -1 into 1. I got -1. So that's why we got -1. You will see a behavior that whenever you use this operator, the bind bitwise not, we will always receive a value less than the value we did. So let's say if I do 8, I'll get -9 with so and if I do -9, I'll get 8. If I do 7, you need to understand this pattern. So see, it's 7. So -7, then -1. What will happen? So the number get converted, it become -7, then we subtract a value. So -8. So -8. Now if I want to convert -7, how it will behave? -7 will become +7 and -1. It will become 6. So 6 will come. So that's how this operator works. Moving forward to the left shift and right shift. This is very simple. Arithmetically, if you will look over them, you will see a very interesting pattern. So whenever I do 4 right 1, you see 2 comes. If I do 8 1, 8 right shift 1, you will see 4 will come. Now what is happening here? As you know, binary equivalent of 4 is what? 1 0 0. And binary. So what happens whenever you use a right shift? So the least significant bit, it just drops by. So what happens? This thing, no wonder it's either 1, it's either 0. This thing will get removed. So what will happen? You will receive. You need to then convert this value into the integer part. So 0 1 0 is what? 4. Not 4 actually, but 2. So what happened when we did 4 right shift 1? It became 2. That simple. Likewise, if we do what? Let's say 7. So if I want to right shift its value by 1, what will happen? This one will go, the remaining will be the result. So this is 1 plus 2, which is 3. So if I try to do 7 right shift 1, I got 3. The solution is very simple. If you want to mathematically select whatever the number is, you just divide it by 2. Just the quotient which you get after removing all the decimal point, that will be your answer. If I do 7 by 2, I'll get 3.5. Just remove this 0.5. You get it 3. Likewise for 8. 8 by 2, the quotient you get, it's 4. The remainder is 0. It's not required. So here we go. Now we come to left shift. In left shift, what happens? The least significant bit is shifted by 1 bit. So 0 will come in that place. This is a left shift. In left shift, the bit is shifted by 1 towards left. A new bit will come which is 0 by default. So now what will be the value? 0 0 0, and this is 2 to the power 2, which is 4. If you do, let's take an example for this so that it will be more clear. So again, let's take 7 for now. So what we want to do, we want to perform this thing. So binary equivalent is this. We are saying that it will move a bit forward. So something like this will happen. So if you convert it back, this is what? This is 2, this 4, sorry, my bad. This is 0 plus 2 plus 4 plus 8 plus again 0. So it is what? 40. If I run this, 14, that's how it works. So mathematically, if you want to say, it is nothing but n into 2. So, and if you want to make it much more generalized, as you can see, there is a number, then you do left shift and another number. This is n1, left shift, n2. So it is nothing but n1 into 2 to the power of n2. So if I do n1 left shift by 0, so what we are expecting? n1 into 2 to the power 0, which is n1 only. So if I do 7 left shift by 0 bits, I should get 7 itself. That's the output we're expecting. If I do 7 left shift by 2 bits, if I do this, so what we will get? 7 to the power 2, which is 7 into 4. So this is what we are expecting. 7 into 4 is nothing but 28. If I try to do this, 28 we get. Likewise, for the right shift, you can make it n1 right shift n2. It's n1 divided by n2. So if I do 7 divided by 4, I get 1. Do 7 right shift 2 times, I'll get 1. That's how it works. So that's how you can calculate whenever you need to solve an expression related to bitwise operator, left shift, right shift. So we have covered all 6 bitwise operators for now. So let's on the screen also here you can see and operator we covered, or XOR, not, left shift, right shift. All 6 we have covered. So let's move forward. I need to Now we will go through binary operators. So binary operators need at least 2 operands. So there will be an operand in front. In between there will be a binary operator. Then on the right also there will be an operand. So a number, some mathematical operator, then another number. So these are our binary operators, which is addition, subtraction, multiplication, division, floor. These are some binary operators. So these are mainly, I have taken example of all the mathematical expression which we do use in our day-to-day programming practices. So we have used addition, multiplication, subtraction, but division and exponent also. But what is floor division and what is modulus? So have a look over the screen. So if I do 7 modulo 2, not modulo but floor division, you will see 3 as output. And if I do 7 m% 2, not m% but percentage 2, I receive 1. If I do one thing, if I do 2 into 3 plus 1, 7 I get. So what am I getting when I'm using modulo? Whenever I'm using modulo, which is this percentage, I always get the remainder of it. So to get a remainder after dividing something, for that we can use this operator, which is the modulo, and for getting the absolute value of the quotient without any decimal, without any remainder, for that we use this double backslash or double division, also known as floor division. So whenever you have a number, let's say I have a number, I have a number 1, 2, 3, and I want to extract its digit. How I will do it? So while number is greater than 0, number here, while number is greater than 0, number should do what? Number should do nothing. We will print number. Now for the remainder we use the modulo number modulo 10, and now what we will do, we will just use this, sorry, we will use this. This is an assignment operator. We will learn it in the upcoming part in this lecture only. I'll try to cover. If the time won't allow us, don't worry, we will still able to understand what is happening. So let's run the terminal. Let's exit this, and let's clear those two. If we run python demo.py, here you will see 3 to 1. These are nothing but the numbers, the digits of this number only. So with help of these operators, you can extract each digit of a number. This will be very useful whenever you will be doing the these equations in arrays, and in arrays or something whenever. So this is a great concept to know. Do make sure that you have a good hold over it. So let's get back to business. Now, these were the binary operators we covered bitwise. Now, there are two interesting operators, which is and is not. These are identity operators, and it tells whether an object is referring to a same memory location or not. Do you remember that we used a ID function to extract the ID of uh, literal? For that you can use is or is not. So for example, as we know that in the previous lecture I did told you about, there's a concept of aliasing. So what is aliasing? Creating another name for the same object. So let's take a list with the name list. I'll add some numbers to it, 1, 2, 3. So this is that was original list. List 1 is equals to list null to list 2 is equals to 1, 2, and 3. Both are same. List will give us this thing. List underscore 1 will give me this thing, and list underscore 2 will give me this. All are having same values. But now if I do extract the IDs of this, here you can see list and list 1. Sorry, Mama. An underscore will come here and here an underscore two. So if I run this, here we will get three IDs. This is 56, this is 56. The first values are common. This is 656, this is also 656. So here you will see these list and list 1 are having same IDs, but list 2 is having different ID. So whenever I'll be performing certain operations, will I use ID function or can I do it in a much cleaner way? Yes, you can use is operator. So list is list 1 if I do. Both of these are referring to same memory location. If I run this, a true will come, a boolean true, which is a keyword which we learned in the previous lecture. Now, if we do list is list 2, false will come because no, they are referring to two different values. We will also learn why this happened in whenever we will start with list. List is a data type. We will cover this in very few upcoming lectures, so don't worry about it. It will be in our lectures very soon. The way we use is we can use is not. So list is not list 2. So this is true list. This list is not the same list as same list 2. So if we will run this, true will come. And if you try to compare it with list 1, false will come. So that's how identity operators work. So let's move forward. Now we have relational operators. These are the operators used to compare values. So whether to check whether either values are equal, not equal, either something is greater than, equal to compare these, we use this symbol. This symbol is for equal to. This is for not equal, and this is for greater than, and this is for less than. This is as similar to as a mathematical operation, but what I need to make you focus on, you need to have a look over this, the second and fifth six. You will easily able to keep in mind that yes, equal to is like this, but sometimes you might put equal to then factorial symbol or the quotient, not the quotient, but the exclamation symbol. And you might put equal first, then greater symbol. So that's not how it works. You need to know that in for greater than or equal to, the symbol comes first, the comparison symbol comes first, then this equal to operator comes. So we will have a look over this with few examples. Let's say I want to check whether 7 is equal to 7. We know 7 is equal to 7. So if I do it, true will come. Is 7 not equal to 7? If I do it, false will come. 7 is equal to 7. So 7 is not equal to 7 is a false statement. So hence we receive the false. Is 7 greater than 7? No. Hence false come. Is 7 less than 7? Also no. Is 7 greater than 5? Yes. Is 7 less than 5? No. Is 5 greater than 7? No. Is 5 less than 7? Yes. So that's how these operators work. And whenever you want to compare, like let's say you have an expression about age, like age should be greater than equal to 18. So for that, you can use this symbol, greater than equal to. Is 7 greater than equal to 7? Yes, it's true. So we will receive true. Likewise, 7 less than equal to 7. Also true. So that's how we use logical operators. We have assignment operators. Assignment operator, this equal to operator. But whenever we use these arithmetic operators, so how it behaves, we will have a look over it. So whenever you do something plus equals to another value y, what does Python do? This is a shorthand form. So The actual equivalent is x plus is equals to y. This x is referring to the older value of x, and this y is referring to the older value of, not the older value, but the value of y. So whenever you will do x plus is equals to y or anything, either you, if you write multiplication here this will become multiplication. If you do minus here, this will become minus. Let's even have a demonstration of this. Let's create a variable x is equals to 7. If I do x plus is equals to 5, now what, by the definition which I explained you, x plus is equals to 7 will do what? The by default I gave 7 this and y 5, and the expression is x plus is equals to 5. This will be, the older value is 7 and this is what? Here it's a addition and here it's a 5. So this will be 12. And if I run it, if I try to extract the value of x, I'll get a 12. Likewise, if I do x equals to 10, the floor division. So by doing floor division, what I'll get? I'll get 1, because not so I'll get a 1. So by doing this, if I try to extract x again, I'll receive 1. If I again make it 12 and I try to do it floor division, I'll receive 2, not floor division, but if I try to extract the remainder with modulo, then I'll receive 2. That's how it works. So these were the assignment operators, which you should know. These will be really helpful whenever you want to simplify your expressions. Even though it's against the Zen of Python, which is explicit is better than implicit, but still you should know about them. Then we have membership operators. We will cover membership operators in the upcoming lectures in a lot more depth. Like not depth, but membership operator is, it tells whether an element exists in a collection literal. In the previous lecture, I told you about a collection literal that we have sets, then list and tuples dictionaries. So these are few collection literals. So if you want to check whether an element exists in a certain collection, you can use them. So I'll just copy the code here, which I kept for the demonstration so that we will save some time. So here it is. Now, if you will have a look for this thing, if I try to run this, here I have written fruits is equals to apple, banana, and mango. And I printed apple in fruits and I printed orange in fruits. So here you know that this is a string literal. So this list contains, list is a collection literal which contains 3 string literals, which is apple, banana, and mango. So apple is in fruits. So the membership operator in will not ask, but it will tell that is apple is in fruit. So as we know that apple is within the fruit, so we got true here. Likewise, orange is not here in the fruits list, so it resulted in false. Here we asked the orange is not in fruits, so it behaved as it is. It, as you know, yes, it's not in the fruits list, so it resulted in true. So this was our membership operators, and there is a concept of operator precedence order. We will practice few more questions over all these operators. So how does these thing like how does Python operates or works uh, over an expression. For that, we need to know that what is the order in which Python give priority to certain operator. So parenthesis is the most important one, then exponential, then the unary, then the multiplication, division, floor, and modulus, then addition, subtraction, then the bitwise, then our comparison operators, then our logical operators. Like this, we have a certain precedence order. So Python, whenever you write an expression, Python evaluates it in this order only. So for that, you should know, whenever there is an expression in front of you, you should know that okay, parentheses will be evaluated first, then the exponential will be evaluated, and whenever there are multiple like same operators within an expression of same value, then what will happen? Python will will start evaluating the expression from left to right for all the operators except one, which is our exponential operator. So for that, Python will start evaluating from right to left. So whenever you will do 2 to the power 3 to the power 2, something like this, you will get a value which will be equivalent to like so you do 2 to the power 3 to the power 2. It won't operate like 2 to the power 3 8 and 8 to the power 2 64. It won't do it like this. What it did 3 to the power 2 first. From right to left, it start operating. It converted it. So 3 to the power 2 got 9, and 2 to the power 9 then it did. Then we received 5 to the power 12 instead of this. Like 2 to the power 3 is 8 and 8 to the power 2 is 64. So not like this. And don't worry about it. Just have a look over these operators and revise it thoroughly. In the upcoming lecture, I'll discuss all these questions. So we will go through these questions and we will have a look over the precedence order also. So that's it for today's lecture. Keep enjoying, keep learning, and do keep practicing.